topic that we're discussing is electromagnetic theory, and we're going to continue with Maxwell's differential equations. So in the previous session, we did Maxwell's first equation that was taken up from Gauss law in electrostatics, and the remaining three equations we're going to be doing in this session. So the next equation comes from Gauss law in magnetostatics, and equation 1 here represents the mathematical form of Gauss law in magnetostatics. You can see that the surface integral of B dot ds equals 0. Now B is the magnetic induction vector, and ds is an elementary surface, and if you integrate it, this actually becomes the flux of magnetic induction vector, and that's actually equal to 0. So as far as mathematics is concerned, this is very easy to see that if you apply the Gauss divergence theorem to equation 1 on the left hand side, then as we discussed earlier, the surface integral can be converted into the volume integral, and when it comes to volume integral, it is the divergence of that vector, the volume integral of the divergence of that vector, of which we're trying to convert. So here B dot ds surface integral actually becomes divergence of B volume integral, and that should be equal to 0. Now we know that volume is arbitrary, so the integrand in equation 2 should vanish. In other words, divergence B equals 0, and that's our equation 3. In fact, this is the second Maxwell's equation. So the first one is from Gauss law in electrostatics, which says that divergence of electric displacement vector is equal to the volume charge density, and this particular equation tells us that divergence of magnetic induction vector is 0. Now if you look at the physical picture, then this is very easy to see. Now divergence is actually 0 for solenoidal fields where the number of the flux lines entering the volume is equal to the flux line leaving the volume. So, and we also know that magnetic field forms loops. So outside, if you talk about a bar magnet, then you can clearly see that outside of the magnet, the lines are traveling from. So if you have a bar magnet, you have a north pole and a south pole. Okay, it's not symmetrical. It's just, let's assume that it is exactly in the center. So we have the magnetic field lines emerging out of the north pole and entering the south pole. And within the magnet, they travel from south to north. So they form continuous loop. And if you take divergence of this, the solenoidal field, that's coming out to be 0. So the divergence of magnetic induction vector is 0. So that's your second equation of Maxwell's. So moving on, the third equation is actually a manifestation of Faraday's law of electromagnetic induction and the induced EMF. So if you remember Faraday's law of electromagnetic induction, it says that the induced EMF in a coil is directly proportional, or it's actually equal to the rate of change of flux across that coil. And you can see there is a negative sign here. This negative sign is due to Lenz's law, which says that the direction of induced EMF is such that it is trying to oppose the change in flux. Whatever direction the flux is changing, the induced EMF is in such a direction that the flux due to the induced EMF will try to arrest the growth of the flux which is causing that induced EMF. So the direction of the induced EMF is such that it opposes the very change which causes it. So equation 1 here actually tells you Faraday's law of electromagnetic induction. Now We also know that we can represent potential as the line integral of electric field. So that's my equation 2, where the electric potential is equal to E dot dl, which is the line integral of electric field. Now if you combine equation 1 and 2, since the left hand sides of both the equations is are equal, so the right hand side should also be equal. So we have line integral of electric field across any closed loop is equal to the rate of change of magnetic flux through that loop, and that's our equation 3. And also we know that magnetic flux is B dot ds, which is the surface integral of B dot ds. And if I replace that, substitute the value of magnetic flux, which is B dot ds, from here back into equation 3, I get my equation 4, where we have the line integral of electric field is negative time rate of change of magnetic induction vector, and that taken across the whole surface. So hence the surface integral. Of course, the negative sign is in tune with Lenz's law. Now, if you look at equation 4, on the left-hand side, we have a line integral. On the right-hand side, we have a surface integral. And what we can do here is apply Stokes' theorem to convert the line integral into the surface integral. If you remember, the Stokes' theorem says that the line integral of a vector is equal to the surface integral of the curl of the very same vector. And that is represented in equation 5. So now we have the surface integral, which is actually the surface integral of curl of E dot dl, and we can plug it back in our equation 4 to get equation 6. So from 4 and 5, we understand that on the left hand side we have the curl of electric field, and that curl is taken over the whole surface. And on the right hand side we have the magnetic flux linked with that surface and the time rate of change of it. So you can combine these two integrals because both of them are surface integrals, and when you combine them you get equation 7, and the right hand side is 0 here. We all know that the surface across which we are trying to find the flux as well as the curl of the electric field around the boundary of that surface itself is arbitrary. And when the surface is arbitrary, the integral on the left hand side would vanish. That is, del cross E plus del B upon del T equals 0, or curl of electric field vector is equal to negative time rate of change of magnetic induction vector linked with that surface. And hence we get equation 3 here. It's not equation 3 actually, it's equation 8. So there's an error here. So this equation actually is Maxwell's third equation, which is obtained from Faraday's law of electromagnetic induction. So that brings us to the last equation of Maxwell's. Now this is slightly complicated because it's derived from Ampere's law, and there is some inconsistency in Ampere's law, which actually leads to a paradox, which can be only resolved by assuming that there is something called displacement current. So we've had that discussion earlier, displacement current, and this particular equation in its crude form, which is the Ampere's law, does not include the displacement current. And this addition was later on made by Maxwell to make this equation consistent. Now we have the Ampere's law, where the line integral of magnetic induction vector, equals mu naught times the current threading through that surface and that loop, the loop of the magnetic field. And we all know that current can be represented by the surface integral of the current density J, and hence I get my equation 1, where on one side we have the line integral of the magnetic field, on the right hand side we have the surface integral of the current density. Now again, on one side we have the line integral, on the other side we have the surface integral. What we can do is we can apply Stokes theorem onto the left hand side and make this equation somewhat homogeneous, and using that we have the curl of induction vector across the whole surface is equal to mu naught times the surface integral of the current density. Now again, since the surface, we combine them both and the surface is arbitrary, and the integrand should vanish, and after that if we rearrange we get the curl of magnetic field vectors equals mu naught j, and if you divide both sides by mu naught, which is the permeability of free space, then we know that B divided by mu naught should give you H, and hence we get this equation del cross H equals J, or curl of H equals the current density, and that is the basic form of Ampere's law as derived by Maxwell, the differential form. But we all know that this is inconsistent, and we can prove that by taking divergence on both sides. So if I take divergence on both sides, then I have on the left hand side divergence of a curl, which is 0. On the right hand side I have divergence of J. So in effect, if I take divergence on both sides, I get the result that divergence of J is 0, which is inconsistent with the continuity equation, because continuity equation says that divergence of J equals the negative time rate of change of volume charge density. So if at all there's a divergence, there has to be a decrease in volume charge density. So it's not consistent with this equation. So we have to assume something, and Maxwell modified Ampere's law and added an additional term which he called the displacement current to the conventional current. So now we have the modified Maxwell's equation, del cross H equals J plus del D, J plus JD, where JD is the displacement current. Now we all know that from the first equation of Maxwell's, that divergence of electric displacement vector equals rho. Now if I take divergence of J, del dot J, just take the divergence of the continuity equation. No, we're not taking divergence of continuity equation. What we're going to do is replace this rho from equation 6. Okay, so replacing the value of rho in equation 6 back into equation 4, which is the continuity equation, I have the divergence of J plus divergence of del D upon del T equals 0, and just factor out divergence, then we have del dot J plus del D upon del T is equal to 0. Now compare this equation with the earlier equation that we had. Okay, so we have here the equation 5. If we compare, let me just get a marker. If we compare this equation with this equation, okay, compare it here. So we have curl of H equals J plus del D upon del T. So you take the divergence of these two equations, take del dot here, okay, and we have del dot here. Compare the two. So this equals del dot, so this equals 0. So we have del dot J plus del, this thing should be equal to del dot J plus del D upon del T. And if you make a comparison, then you find that this del D upon del T should be equal to JD. So this del D upon del T is basically the displacement current. This term is actually equal to JD. You compare these two equations. So that is the actual form of Maxwell's fourth equation, and this is, you can see that it's very consistent with the equation of continuity. So instead of having only J, we have another term here, del D upon del T, which is the displacement current, which happens due to change in electric flux across a given volume. So with that, we have concluded all the four equations. We have derived them. And now in our next lecture, we're going to combine these equations, form a coupled differential equation, and finally arrive at equations for electromagnetic wave in free space, or even for that matter, dielectric medium or conducting medium. So I'll see you in the next. Thank you.